There are a couple of applications for inductors and capacitors that make for some useful and kind of different circuits. And so the first one that I want to discuss is the integrator circuit. We mentioned this in the chapter on op amps, but it's possible in the op amp to use a capacitor in order to form some mathematical functions, and one function is the integrator. So let's look at the circuit before we talk about the equation. So on the left is our inverting amplifier circuit, where, if you recall, the output voltage is negative RF over RI times the input voltage. So if instead of, and remember, 0 amps coming in here at the inverting input, so no current into the op amp. If we, instead of that, if we take the resistor that was in the feedback loop and we replace it with a capacitor, then we still have our current through the resistor and we have our current through the capacitor. And given that we have 0 current into the inverting amplifier, the resistor current can be defined as V input over R. The capacitor current is minus C dV out dt. And so we can combine these two by setting them equal, since if we looked right here and wrote a KCL, then they would be equal. So if we did that, then we have VI over R is minus C dV dt, and if we do a little rearranging, we get an expression that puts the derivative of the voltage equal to minus 1 over RC times VI dt. And then if we integrate both sides of this equation, we end up with the following expression. Assuming that we have 0 initial condition on the capacitor, in other words, assuming the capacitor is sitting there uncharged initially, then we can write that equation as the equation that we see here in the box. So basically what this circuit does is whatever signal is coming in here at the input, it integrates it, and that's what you get for the output. So I did mention that at one time op amps were considered analog computers, and this is one of the reasons why, is you can end up doing mathematical operations on op amps. We saw the summer, now we see the integrator. Now let me talk a little bit about integrator circuits. You don't really want to use an integrator circuit if you have a DC input voltage. Why is that? Well, if you integrate a constant, what do you get? You get a ramp. And so eventually you get a straight line. And so eventually your output voltage will just, if you have a constant input, your output voltage looks like this. And as time increases, your voltage just grows unbounded. So you wouldn't want to use an integrator circuit if you have a DC voltage input. On the other hand, if you have an input that's very noisy, so let's say your voltage, let's say your input voltage looks like that, then what the integrator does is it will smooth. It has the effect of smoothing. The reason for that is, of course, what an integral does is an integral takes like the sum of the area. And so basically that has the effect of then making the output look smoother. So when your input looks like this, your output, a lot of these little it'll just be smoother and it'll have a little delay. You won't see these like little localized spiky things as much with an integrator. So a lot of times an integrator is used to smooth out or eliminate spiky electrical noise. We can also build a differentiator. In the case of the differentiator, you just flip where the capacitor is placed, and so in this example, the capacitor is placed where the input resistor occurs, and so it's a little more straightforward derivation. You have the capacitor here, so in this case your input current is C dV dt. Your current through your resistor is minus V naught over R. You set those equal and you find that the output takes the derivative of the input. This is less commonly used for the very reason that we talked about with the integrator circuit. On the integrator circuit, if you put in a very noisy signal, integration has the effect of eliminating or smoothing out that noise. With a differentiator circuit, if you put in a signal that has a lot of spiky, rapid changes, remember the derivative is proportional to the slope. So if you put in something that has a lot of very rapid, noisy, spiky looking stuff in the signal, then basically what this differentiator is going to do is it's going to exacerbate that noise. You'll get an even noisier signal out. What the differentiator is useful at doing is if you want to block DC. So oftentimes on your input, what this capacitor does, because remember a capacitor looks like an open circuit at DC, so a capacitor will block a DC voltage signal. So, and of course, as you know, the derivative of a constant is equal to 0. So if you have issues with DC that in a signal that you don't want, you can use a differentiator to get rid of the DC and pass the non-DC part of the signal. So two little circuits showing you, first of all, some of the applications of op amps as well as some of the applications of capacitors. You notice in our circuits we're using capacitors and not inductors, so the question is, could you build an integrator and a differentiator with an inductor? And the answer is yes. What happens is the inductor would be in the opposite position of where the capacitor is. So for the differentiator, the inductor is in the feedback loop and the resistors in the input loop, and for the integrator, the opposite. Now, that's not commonly done for a couple of reasons. First of all, inductors tend to be large physically, and so it's certainly difficult to manufacture them in a chip, and even sometimes hard to breadboard those. And then inductors just tend to be overall more difficult to procure commercially. So sometimes you would have to wind your own, and so typically, given that it'll accomplish the same thing and is significantly smaller and easier to find, capacitors are used in differentiator and integrator circuits. So that concludes the background and overview sections, the theoretical parts of talking about inductors and capacitors. We'll make a couple of quick videos that show some examples on how to do calculations that will be helpful in the homework.